The differential forms of the fundamental laws tutorial number 4. Consider steady, laminar and incompressible fluid flow between two fixed vertical parallel plates. If the fluid is moving downward between the two plates using the Navier-Stokes equation to determine an expression for the velocity profile, we could take vertical axis is an x-axis to ease our calculation. So in this question, they will give us a similar situation with the previous tutorial in tutorial number 3. However, the direction is in vertical. So we could imagine that we have two walls here. And normally, if in vertical direction, the wall will be fixed because the fluid between these two fixed walls will flow naturally from top to the bottom according to the gravity effect. So means that in this calculation, the value of gravity is exists. We cannot neglect the value of gravity. So normally, you could use the vertical axis here as axis because the terms of Navier-Stokes for x, y, and z is actually the same terms. So we could use the x direction for the vertical one here. And you need to remember that the component of gravity is exists in this calculation. So this is the x direction of Navier-Stokes equation. So I hope you could remember and write it down very well. So we make assumption to ease our calculation. The most common one is we take it as one-dimensional. So the value of v and the value of w will equal to 0. It is steady state. So the value of du over dt is equal to 0. It is incompressible flow, so the P is the rho, the density is constant. It is also a fully developed flow. Del u over del x will become equal to 0. So we substitute all the assumption in our Navier-Stokes equation. We could simplify that Navier-Stokes equation here is 0 equal to negative rho gx minus del p over del x plus mu del square u over del y square. Please remember again, we use the x direction of Navier-Stokes equation here, but we must take the effect of gravity is not equal to 0 because it is actually the vertical one, so the gravity is act on this situation. So we bring the value of mu del square u over del y square to the left side, so we have the positive terms in left and right side here. So we split the power of 2 here by having del over del y. Del u over del y equal 1 over mu. So we bring the dynamic viscosity to the right hand side terms here. So we have this term, and then we bring the value of dy here to the right side. So we have the d del u over del y, and we have this term with del y here. So we do the integral method. We integrate both sides, so we have integration of this one and integration of this one. So we have the integration of del u over del y will give us del u over del y, and the integration of these terms will give us the term of itself, 1 over mu del p over del x plus rho g y, because we integrate with y here, and the constant. So we name the constant here is C1. So we bring the dy here to the right hand side. So we have this term. Again, we integrate both sides. So we have this term. And at these final terms, we have C1y here, and we have another new constant which is C2. And now we need to calculate, we need to determine what is the value of C1 and what is the value of C2 by using the boundary condition. So this is the fixed wall that we have. So let's say this is point number 1 and this is point number 2. As I mentioned in previous tutorial, so the boundary condition means the condition at the boundary of the fluid. So means that the condition at this point and at this point. So let's say we have the gap here is h. So we take this is the origin. So at point number 1, y is equal to 0 and the velocity is also equal to 0 because it is no slip condition here. Or you could write uy is equal to 0. At point number 2 here, the y is equal to h because the gap of these two plates is equal to h. So the coordinate at point number 2, we could take y equal to h and the velocity is also equal to 0 because no slip condition also occur at this point. So we will use this condition, substitute into the velocity terms that we get previously. So we could get at condition y equal to 0 and u equal to 0, the equation 1 become C2 equal to 0. And if we substitute the value of y equal h and u equal to 0, the equation 1 will become C1 equal minus 1 over 2 mu del rho over del x plus rho g h. And then this is the value of C2 and this is the value of C1. We need to substitute to the velocity expression. So we could get these terms and we could simplify it as this one. So this is the final answer for the velocity profile for that situation.